All right, today we're going to talk about double and half angle identities. These are two identities that you'll use a ton in calculus next year, particularly the double angle ones. A little bit of review, these are the sum identities that we've covered previously. So we're going to use these sum identities to derive the double angles first. So instead of writing this as sine of 2x, we're going to rewrite it as a sine of the sum of x plus x. And we're going to use the sum identity above right here to see if we can rewrite it. So this becomes the sine of x cosine x plus cosine x sine x. And just rearranging terms, we'll rewrite this as 2 sine x cosine x. We're going to do the same thing for tangent. We're going to rewrite that as tangent of x plus x. And then use the identity above to see if we can simplify it. So tangent of x plus tangent of x all over 1 minus the tangent of x times the tangent of x. And that gives us 2 tangent x all over 1 minus tangent squared x. And lastly, our cosine one. There's actually 3 different versions of this, and you definitely want to be able to derive all 3 of them because they're all useful. So we'll repeat this kind of the same pattern we did previously, where we rewrote cosine of 2x as cosine of x plus x. And we'll use the identity above, and we get cosine x minus sine of x sine of x. Or obviously cosine squared x minus sine squared x. And that's your first of the 3 versions of the double angle identity for cosine. Now we're going to manipulate that identity using the Pythagorean identity we already know. And we know cosine squared x plus sine squared x is equal to 1. I'm going to rearrange some of these terms here. Let's solve for cosine squared first. So cosine squared x is 1 minus sine squared x. And if we wanted to solve for sine, we would have said sine squared x is equal to 1 minus cosine squared x. We're going to use each of these substitutions to be able to derive the second and third version of the double angle for cosine. So let's substitute first for cosine. We know this cosine squared is 1 minus sine squared. And we can replace that and then simplify. This is 1 minus 2 sine squared x. So that's the second identity. And if we had, instead of replacing the cosine squared, if we had replaced the sine squared, we would have gotten from, and again, we're just looking at the original, if we had replaced the cosine squared, or excuse me, the sine squared with 1 minus cosine squared x, and simplify that, make sure you distribute the negative through, we wind up getting 2 cosine squared x minus 1. And those are the 3 different identities that are the double angle for cosine. I've written those down here. Feel free to pause the video and copy them into your notes as you see fit. So let's talk about how to use the double angle formulas for sine, cosine, and tangent. Our first example deals with an angle in quadrant 1. It says we know sine of theta is 3/4 and theta is in quadrant 1. Let's talk about what that means quickly. So we know if theta is in quadrant 1, it has to be between 0 and pi over 2. Now we're evaluating the sine, cosine, and tangent of 2 theta. So if I double everything, 2 theta has to be between 0 and pi, which means it's either in quadrant 1 still, or it could be in quadrant 2. So if you think about quadrant 1 and quadrant 2, the sign of each of these trig functions you should know. So if it's in quadrant 1 or quadrant 2, sine would be positive no matter what. Quadrant 1, cosine would be positive. Quadrant 2, cosine would be negative. And for tangent, quadrant 1, tangent would be positive, and quadrant 2, tangent would be negative. So we don't quite know the signs of cosine and tangent yet, but we will once we evaluate it. So we need to draw a triangle here. And again, it was given that it was in quadrant 1. Let's label theta on the inside. And they said the sine was 3/4 opposite over hypotenuse. Using the Pythagorean theorem, 16 minus 9. We get root 7 for our third side. So using our identities in that triangle, we're going to evaluate sine first. We know sine of 2 theta is 2 sine theta cosine theta. And sine theta is 3/4. And cosine theta is root 7 over 4. And this winds up simplifying, looks like 6 root 7 over 16, or 3 root 7 over 8. And that should make sense. Again, remember we said sine is positive because we are either in quadrant 1 or quadrant 2. Now you have a bunch of choices. You have 3 different choices for cosine. I would encourage you to use one that uses what is given. So of the 3 identities, I'm going to choose 1 minus 2 sine squared, since I know the sine of theta is 3/4. And even if I made a mistake in my triangle, at least I could get this portion of the problem correct. So let's evaluate this. We know that sine of theta is 3/4, and make sure we square it. So we get 1 minus 2 times 9/16. And that winds up being 1 minus 18/16, or negative 2/16, which is negative 1/8. All right, for the third one, we know tangent of 2 theta, that's equal to 2 tangent theta over 1 minus tangent squared theta. And we're going to make our substitutions here. And we get 2. Tangent theta is 3 over root 7. Over 1 minus 3 over root 7 squared. So if we simplify this, it looks like we get 6 over root 7. All over 1 minus, looks like 9/7. So we get a negative 2/7 in our denominator. I'm just going to multiply by the reciprocal. We wind up getting, looks like 6 over root 7 times negative 7/2. And once you simplify this, it looks like we get negative 21 over root 7, and rationalize. Our final answer is negative 3 root 7 when we reduce. So think about what's going on here. Sine is positive, cosine is negative, and tangent's negative. Clearly we're in quadrant 2. And you want to say something to the fact of sine of 2 theta is positive, and cosine of 2 theta is negative. And that would be enough information to prove that. And there's a way you can check this too. if you wanted to check your answers to make sure that they made sense and that we were in the right quadrants, we know that theta is equal to the inverse sine of 3/4. And if you did that on a calculator in degree mode, you would get 48.6 degrees, which means that 2 theta would be twice that, or 97.2 degrees, and clearly that is in quadrant 2. And that's kind of confirms our suspicion that it was in quadrant 2 from our work. All right, here are the half angle identities. Feel free to pause the video and copy them into your notes. We will use these, it's kind of the opposite direction of the double angle formulas. We'll do a few examples of these and give you some time to practice. All right, let's take a look at some half angle examples. So first one says cosine of 7 pi over 8. That's clearly not on our unit circle. But if we multiplied that angle by 2, we would wind up with 7 pi over 4. And that is something we can clearly evaluate. One of the things you want to point out is that there is a plus or minus in every single one of these formulas. And to be able to evaluate which one it is, it's not both, it's either a positive or a negative. You need to choose which quadrant that angle terminates in. So when we're trying to evaluate the cosine of 7 pi over 8, we know that that angle, 7 pi over 8, is in the second quadrant, and cosine is negative in quadrant 2. So we're going to use the half angle formula for cosine, and we're going to choose the negative, not the positive or negative, just the negative version. So it's equal to the square root of 1 plus cosine of theta. And here, remember with the formula, because we're making the transition from theta over 2 to theta, from the left side to the right side, we have to double the angle that we're trying to evaluate. So instead of 7 pi over 8, I'm going to write 7 pi over 4. And that is all over 2 underneath the radical. So we can evaluate that, and we wind up getting cosine of 7 pi over 4 is negative root 2 over 2. Or excuse me, positive root 2 over 2. And you can simplify that by using baby fractions, multiplying top and bottom by 2. You wind up getting square root of 2 plus root 2 all over 4. And again, we know it's negative because it is in quadrant 2. And what this allows us to do is, knowing that 7 pi over 8 is not on our unit circle, by doubling it and finding that we can evaluate 7 pi over 4, we can now evaluate the cosine of that angle. Let's try the same thing for sine of pi over 12. And again, when we're evaluating this, pi over 12, think about where that is. We're in quadrant 1. So sine is positive. In quadrant 1, we are going to choose the positive formula for this. So I have 1 minus the cosine of 2 times pi over 12. 2 times pi over 12 would be pi over 6. And again, that is an angle that we can evaluate because it's on our unit circle. And so we simplify. So we get the square root of 1 minus root 3 over 2 divided by 2. And we use baby fractions again, multiplying top and bottom by 2. We wind up with square root of square root of 2 minus or plus root 3 over 4. All right, for tangent, same situation. Think about what quadrant you're in here, 9 pi over 8. 9 pi over 8 is quadrant 3, so we know tangent is positive in quadrant 3. So we're going to choose the positive portion of the formula. And let's do 1 minus cosine of theta. And that would be 9 pi over 4 over 1 plus cosine of 9 pi over 4. And again, we're doubling that angle from 9 pi over 8 to 9 pi over 4. Notice that 9 pi over 4 and pi over 4 are coterminal. So we'll essentially evaluate that at pi over 4 instead of 9 pi over 4. We're going to get the same answer. So when we evaluate that, we wind up with 1 minus root 2 over 2 over 1 plus root 2 over 2. Baby fractions gives us, multiplying top and bottom by 2, we get 2 minus root 2 over 2 plus root 2. So at this point, I'd encourage you to pause the video and see if you can tackle question 4. All right, let's take a look at this last problem. So they give us the fact that sine of x is negative 0.6, and we're in quadrant 4. So let's draw a picture briefly in quadrant 4. I'll draw a triangle. And again, that angle there is x on the outside. And let's label that. We have a triangle, looks like opposite over hypotenuse, and it's a 3, 4, 5 right triangle, so we've labeled all 3 sides. So when we're evaluating this, I want to make sure we understand that this is x that we labeled, but we're evaluating the sine of x over 2, cosine of x over 2, and tangent of x over 2, which is half as big as this angle. So looking over here on the right, if x is between 3 pi over 2 and 2 pi because it's in the 4th quadrant, if we take half of that angle, dividing all 3 by 2, we get x over 2 has to be between 3 pi over 4 and pi. Now 3 pi over 4 and pi are definitely in quadrant 2, so we know our angle is going to be in quadrant 2. So that tells us that sine is going to be positive, cosine is going to be negative, and tangent is going to be negative. So we know that before we even start the problem. So let's see if we can use some of these identities. And so we're going to say sine is positive in quadrant 2. Square root of 1 minus cosine x over 2. And we know cosine x, based upon the triangle up top, looks like our cosine is 4/5. So we get the square root of 1/10, or really root 10 over 10. So for cosine, we know cosine is negative in quadrant 2. We're just going to follow the same formula, and we get 1 plus 4/5 over 2. So 9/5 over 2, or 9/10. You can rationalize this. We wind up getting negative 3 over root 10, or negative 3 root 10 over 10. For tangent, we're just following the same formula, and again, we're choosing the negative one because tangent is negative in quadrant 2. We're substituting in cosine, 4/5 for cosine in both the numerator and denominator. And this winds up being, looks like 1/5 over 9/5, or the negative square root of 1/9, which we know is negative 1/3. So we got an answer there. There's also a different way you could have done it. Instead of using that identity, we could have said tangent of x over 2 is equal to the sine of x over 2 divided by the cosine of x over 2. And we knew that those were the previous two answers where we got root 10 over 10 and negative 3 root 10 over 10 respectively. And if you divide those two, you end up getting negative 1/3 as well. That's probably the fastest way to do it, but if we just asked you to find a tangent, you would use the formula directly.